so let's start off with an introduction to thermodynamics. This is going to be measuring the transfer of heat, and one of the ways we measure heat being transferred is using calorimetry. So you're going to need to know how to use joules and calories. These are the two main units we use. 1 calorie is based on, it's the amount of heat that's required to heat 1 gram of water by 1 degree Celsius. And we can relate calories to joules using this conversion, that 1 calorie is equal to 4.184 joules. So as soon as you see this, hopefully you think that if you have a certain number of calories, X calories, and you need to convert them to joules, you know you're going to put calories in the bottom and joules on the top. And you know that 1 calorie is equal to 4.184 joules. So that's your conversion factor. And one thing to watch out for is that there's calories and there's kilocalories. Calories have a lowercase c and kilocalories have an uppercase C. That's unfortunate, it can be a little confusing, but try to remember that if you see the big C, it's a kilocalorie, and that 1,000 calories is equal to 1 kilocalorie. So, let's see. The equation we use for calorimetry, and by the way, calor is heat, metry to measure, so measuring heat, is going to be Q equals mc delta T. You can find it on the sheet you use in AP. Q is going to be heat, and we measure that in joules for the most part, or calories as we saw. M is going to be the mass measured in grams. C is the specific heat capacity. If you're measuring this in joules, then you'll have your specific heat capacity in joules per gram degree Celsius. If you're given this in calories per gram degree Celsius, then you're going to want to have your heat measured in calories as well. And change in temperature is going to be the final temperature minus the initial temperature, and we can measure it in Celsius or in Kelvin. And the reason is that if you change by 100 degrees Celsius, let's say you start at freezing water, that's 0 Celsius, and you heat the water up to boiling, that's 100, it would be the same as if you started with freezing water, so that would be 273 Kelvin. And if we heat it up till it was boiling, we know that to go from Celsius to Kelvin, we add 300 or 273, so we get 373. You can see that to take water from freezing to boiling is 100 degrees Celsius. It's also 100 degree Kelvin. So even though they're different numbers, the size of the degree is the same. So a change by 1 Celsius is a change by 1 Kelvin. So here is a problem that uses Q equals mc delta T. We can see that we're given Q, 255 joules of heat, that's Q, are added to 50 grams, that's going to be my mass, 50 gram piece of metal. The metal changes in temperature from 25 degrees Celsius to 28 degrees Celsius. So this is going to be my initial temperature, and this is my final temperature. And it says, what is the specific heat of the metal? So I'm looking for C. So even if I didn't have the equation at the top telling me what I'd be using, I can see that I've got Q, M, C, and a couple temperatures, so I know that I'll be using that equation. I can see that I'm solving for the C, so I want to get the C alone. I'll undo what's being done to it. I'll divide both sides by m delta T. So m delta T divided by m delta T is just 1. So C equals the joules divided by the mass times the change in temp. So that's the joules divided by the mass, 50 grams, and the change in temp. So the change in temp was the final minus the initial, that's 3.0. Okay, and when I calculate that, I end up getting 1.7 joules per gram degree Celsius. Okay, and that's going to be my specific heat capacity. I give it 2 sig figs because the change in here is going to be 3.0, so that has 2 sig figs. We also use Q equals Cm delta T with calorimetry. So one thing that we can do in lab is use a coffee cup calorimeter. The way this works is we have a certain amount of water in here. We can measure the mass of the water. It's at a certain temperature. We also know the temperature of the water. So we've got the M and we've got the T. We can get the final temperature, which is the change in temp. And we know the specific heat of water. That was that 4.184 joules being required to change 1 1 gram of water by 1 degree Celsius. So we have the specific heat as well. So knowing the mass, the change in temp, and the specific heat of water that are in this calorimeter, we can add a chemical that undergoes a reaction, or we can add a hot piece of metal that's going to be giving off heat, and we can measure how much the water changes in temp and actually calculate how many joules were gained by the water inside the coffee cup. And that'll tell us how many joules were lost by whatever we placed inside the coffee cup. So here's an example. I have a 2.5 gram, so that's the mass of my metal, 2.5 gram sample of a metal at 100 degrees Celsius. So this is the initial temperature of the metal. It's dropped into 50 milliliters of water, and since 1 gram of water is 1 milliliter of water, this is also my mass. It's 50 grams of water. And it's at 25 degrees Celsius, so this is the initial temperature of the water. The question is, what will the final temperature be? So I'm looking for TF. And TF will be the same because the metal is losing heat to the water because it's a higher temperature, and the water is gaining heat from the metal until they get to the same temperature. Once they're there, they're going to be in equilibrium. So I'm looking, I have the specific heat capacity of the metal is this, and I didn't write it, but I know that the specific heat of water is 4.184 joules per gram degree Celsius. So what we said was the metal is losing heat, and it's losing heat to the water. So the heat lost by the metal is the same size as the amount of heat gained by the water, but their opposite changes. This has a negative loss, has a loss of heat, and this has a gain. So if I put a negative sign here, they're the same amount, but they're opposite sign. Okay. And since I know that Q is equal to Cm delta T, or MC delta T, either way, but on your sheet it's MC delta T, then I can just plug that in for this side. I can say that the mass of the metal times the specific heat of the metal times the change in temperature of the metal are going to be equal to the mass of the water times the specific heat of the water times the change in temperature of the water. And now I can plug in for those values. And I can say, let's see, the mass of my metal is 2.5 grams. Oh, I left out this negative. They're equal, but they're opposite. Okay, so I have 2.5 grams of the metal. The specific heat of the metal is 1.2, and that's joules per gram degree Celsius. And the change in temperature is going to be the final minus the initial. I'm looking for that final. And I know the initial was 100 degrees Celsius. So that's all equal to the opposite, the negative, of the mass of the water, which was 50 grams, times the specific heat of the water, 4.184 joules per gram degree Celsius, times the change in temp of the water. So same thing, I know the final temperature is going to be the same as over here because they come to the same temperature. I don't know the final, so final minus initial. I know the initial was 25 degrees Celsius. Okay. And at this point, you just have some algebra. You're going to multiply these three things together. So TF times 1.2 and times 2.5, and 100 times 1.2 and the 2.5. And after doing that, you're going to get, we have 3TF, and the units for that are going to be, so the grams cancels out right there, and I'm going to be left with joules per Celsius. So 3 joules per Celsius TF. Okay, and that's going to be minus this guy, which is going to be 300. And the units there, this was Celsius, so that Celsius will cancel out in this one, and I'll just be left with 300 joules. So that's equal to, same thing, I'll multiply these times the TF, and this one's going to be negative. And so I do that, and I get negative 209.2, and my units are going to be, say the grams cancels out, so I've got joules over Celsius, TF. And I'll do the same thing with the 25, multiply by those two, and I get 5,230, and that's joules. You might have noticed there's a negative sign here and I put a positive. It's because this whole term has a negative sign applied here. So that becomes positive. Okay, so now I want to collect like terms. So what I'll do is I'll go ahead and add 300 to each side. So 300 joules plus that 5,230, and I get 5,530 joules are going to be equal to, I'll add 209.2 joules per Celsius TF, and I get 212.2 joules per Celsius TF. Trying to get the TF alone, so I'm going to divide both sides. First I'm going to do that. I'll divide both sides by 212.2 joules per Celsius. Divided by 212.2 joules per Celsius. And I can see the joules are going to cancel out. That's good. Actually, this will all cancel out. And I can see joules will cancel out here, and I'm left with 1 over Celsius. So we know if it's in the bottom, if it's in the denominator of a fraction, and I'm dividing by this, it's going to pop up into the numerator. So I'm solving for the final temperature in terms of Celsius, which is good. Final temperature is this divided by this, which I get 26.06. And I should go ahead and look back at sig figs. I didn't do the sig figs perfectly, so I'm not going to apply all the steps. I'll just say there's 2 here, so I'm going to say 26 degrees. And I would plug that in to see if I got the answer right. I would plug it in right here and see if this side is equal to this side. So next.